Hello friends, today I have come up with a new topic, impedance matching and tuning. You might have heard about matched loads, mismatched loads, and your microwave engineering. And what is the problem with the mismatched load? Why you call a load as mismatched and why you call a load as a matched load? So let's see. Suppose you have a transmission line with the characteristic impedance Z0 and you are connecting a load having impedance ZL across the transmission line such that this load impedance is not equal to Z0. Then what will happen? At the point where you have connected your load to the transmission line, some part of the power will reflect back to our load, which is undesirable. Some part of your input signal will be reflected back toward your source. So this is the case of mismatching. What is our target? What is our objective? Our objective is to transmit the power fully from source to load without any reflection. How we can avoid this reflection? Means that no reflection. You have reflection coefficient 0. It means that your load is now matched to the transmission line. It means that ZL now became equal to Z0. There is no longer mismatching. We can obtain this matching by using impedance matching circuits. We insert these impedance matching circuits in between your load and your transmission line. So again, look, in this topic we will study about all the possible impedance matching circuits, and in the next video we will also study about impedance matching circuit designing and how to use Smith chart to solve the problems to design different impedance matching circuits. Now remember one thing, this load ZL must have a non-zero real part in order to make your circuit matched. What I mean to say is this load has two parts, real and imaginary, and this real part of the load should never be zero. Okay, then you can finally match your load to the transmission line. So let's talk about types of impedance matching circuits. There are many types of impedance matching circuits which are available. There must be some criteria on the basis of which we will select one of the impedance matching circuit out of many available. Did you understand why we need this decision criteria? So I'm going to tell you about those decisive factors on the basis of which we are going to select our impedance matching circuits, and those decision criteria are complexity of the impedance matching circuit, how much our matching circuit is complex. The more complex our matching circuit, the more there will be losses, and so we try to come up with simple designs, simple circuits which can solve our problem. Second thing is bandwidth, how much of the bandwidth this particular impedance matching circuit is supporting. Then we look into the implementation, how easy to implement this impedance matching circuit in particular transmission line. Suppose you have waveguides, you have microstrip transmission line, coaxial. So in different scenarios, how to implement these matching impedance matching circuits, and which one will be the best option. And of course, the fourth factor is adjustability. Adjustability, if you have a load which is variable, so in such a case, which type of impedance matching circuit is flexible enough to match that variable load. Remember one thing, these all matching circuits gives you a reflection coefficient value 0, means that perfect matching at only one particular frequency. It cannot give you reflection coefficient value 0 at all frequencies, just one frequency. That's why the term bandwidth here encounters how we will define the bandwidth. First, to understand bandwidth of the impedance matching circuit, we have to talk about the reflection coefficient. As you know that the value of reflection coefficient ranges from 0 to 1. When there will be no mismatching, the value will be 0, and when there will be mismatching, the value will be 1. So as I told you that there will be only one frequency at which you will get reflection coefficient equal to 0. What about the other frequencies? At other frequencies, this reflection coefficient value will start increasing from 0. So normally we accept all those frequency ranges for which the value of reflection coefficient is less than or equal to 0.2. So this will make our bandwidth. That range of frequencies for which the reflection coefficient value is 0.2 will be the bandwidth of the impedance matching circuit. Now coming toward the type of impedance matching circuit. The first type, lumped element network, also called L networks. Actually, these are a combination of capacitors and inductors. We use capacitor and inductors, and we can come up with different designs, but there are limitations of each of these impedance matching circuits. For example, if you are working in very high frequency ranges, then these lumped element networks will not be appropriate, because you know that the properties of inductor deviate from its normal behavior at very high frequencies. The second type is stub matching network, and in stub matching network we have two types: single stub matching and double stub matching. First, let me clear you what is stub. Stub is nothing, just a piece of transmission line which is either short circuited or open circuited. And you may know from the topic of transmission line theory that these stubs will give us a pure imaginary value of impedance. So why we are using double stubs? A single stub has its own limitation, but we can overcome those limitations by using double stub. The third type of impedance matching circuit is quarter wave transformer. Quarter wave transformer is again a piece of transmission line. This is your transmission line with characteristic impedance Z0, and this is your load ZL. What is quarter wave transformer? So in between this load and transmission line, you will just connect a piece of transmission line with the length lambda by 4, and the impedance of this transmission line piece of transmission line is let Z1, and this Z1 should be the geometric mean of Z0 and ZA. Normally we consider these transmission lines as lossless, so Z0 and Z1 are real numbers. And the important thing about the quarter wave transformers are that these are used for matching in such loads where the ZL is pure resistive, means that XL part of the load will be 0, and quarter wave transformer will work for such loads ZL, RL, some real value. So there are two types of quarter wave transformer: single section quarter wave transformer and a multi-section quarter wave transformer. In multi-section quarter wave transformer, we use different sections of quarter wave transformers, each of length lambda by 4, and the characteristic impedance may be Z1, Z2, Z3, and so on. The purpose for using the multi-section quarter wave transformer is just to improve the bandwidth. We can obtain a greater bandwidth by using multi-section quarter wave transformer as compared to single section quarter wave transformer. Again, remember, these all matching circuits gives you a reflection coefficient value of 0 at only one frequency. So hope that you like the video. If you like the video, please subscribe and share. It will encourage me to make more and more videos for you, and thank you for watching the video. See you soon.